Okay, so let's get started. Hello and welcome everyone to the fifth week of interactive live sessions for the course Fundamentals of Convective Heat Transfer. It's being offered by NPTEL, being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm the TA for this course. So, like every other week, we shall be solving some problems together. So, without any further ado, let's get started. Uh, so this week our discussion has been on internal flows and convective heat transfer within them. So one of the cases of internal flows is flows through a pipe, a circular pipe. So this question relates to that. It is asking us that in a circular tube, the nature of fully developed velocity profile. So here this word is necessary. A fully developed velocity profile for laminar flow is it option A, linear, option B, parabolic, or option C, flat, or option D, exponential? So if I take a pipe like this, a circular one, then there will be certainly a developing region where the velocity profiles will be changing. And after that, when it becomes fully developed, there will be one particular shape of a velocity profile. The question is asking us is what that velocity profile is mathematically. Is it option A linear? Is it option B parabolic? Is it option C flat? Or is it option D exponential? So let's take a look at the solution. It is actually parabolic. So this is something that we have learned. So if I draw a cross section like this, so this is the center line. The velocity profile usually takes a parabolic form when it's fully developed, something like this. We know that it is, so this, okay, uh, this is the x direction, the axial direction, or let's call it z. This is the radial direction r, and this is the azimuthal direction given by, let's say, something like p or theta. In this case, we'll take p. So r, phi, z coordinates are the cylindrical polar coordinates. In that, our axial velocity uz varies only as a function of r and is given by 2 into u maximum. So this value over here, this is u maximum. Sorry, not 2, just u, uh, u max, I'll call it. Sorry. So u max multiplied by 1 minus r over r naught squared, whole squared, where r naught is the radius of this pipe. So as you can see, if r equal to r naught, then this becomes 1 and 1 minus 1 becomes 0. So that satisfies the no slip boundary condition. That is, at the wall, there will be 0 velocity. And when radius is 0, that is at the center line, then this term becomes 1 and we get u is equal to u max, this value. So the maximum is at the center line. So let's move along. We'll move on to question number 2 now, which is asking us to consider the following statements. So there are 3 statements given here, 1, 2, and 3, about developing flow. So earlier we saw the fully developed flow. Now we will look at developing flow inside a circular tube once again. So the statements are as follows. Statement 1 says that the core velocity increases in the axial direction. The core velocity means the velocity at the center line you can consider, or in the region where boundary layer hasn't reached. So I'll just draw a figure to demonstrate the point. So once again, I have a cylindrical tube like this, with this being the center line. And what happens is boundary layers grow like this, and that is what we mean by development of flow. So this region is the core region. So the velocity in the core region is called core velocity. The question is whether the statement is that core velocity increases in the axial direction. And once again, this is our axial direction Z, radial direction R, and azimuthal direction P. So then we come to statement number 2, which says that the boundary layer thickness is equal to the radius of the tube in the developing flow region. And statement 3 says the radial velocity component is 0. Once again, these are all pertaining to the developing region. So what I mean by developing region is up to this much. So from the entry till the entrance length, the hydrodynamic entrance length. This is where there is developing flow, DF. And after that, we have fully developed flow. I will call that FDF. So consider all these three statements, find out which ones are correct or wrong, and then in the options given below from A to B, we have different combinations of option A telling us that only statement 1 is correct, option B says only statement 2 is correct, option C says that both 1 and 2 are correct, and by definition 3 is incorrect, or is it option D that 1, 2, 3, all of them are correct? So first figure out which statements are true or false and then find out the correct combination from the four options given below. Let's take a look at the solution. It is actually option A, that is only one is correct. So the core velocity increases in the axial direction. So let's go back to the previous slide. So yeah, here this shaded region which I've marked, that is the core region. And as it turns out that, in the entrance there is a plug flow velocity profile that we have the same velocity throughout, right? Something like this. Then as it develops, as it turns out that in the boundary layer region, the flow is slowed down, right? Due to the no-slip boundary condition and viscosity within the layers of the fluid. And as a result of that, to maintain the same mass flow rate, the core has to move with a higher velocity. So I'll pictorially depict this in a different way. So the core velocity would be higher than what it started out. So there will be a slowing down in this region and an acceleration in the core region. So due to that, core velocity actually does increase in the axial direction because as we move forward, so this is, let's say, at some section B, and if I draw another section at, I'll call that section A, which is, uh, you know, uh, upstream of section B, there the axial velocity won't be as much. So here, something like this. So here also it will increase from the starting, which let's call that section O. So the core velocity, I'll call that BC at O, that is less than what is that at A, and that is even less than what is that at B. So as we move forward in the axial direction, the core velocity increases. So which is why statement 1 is true. Now, statement 2 says that the boundary layer thickness is equal to the radius of the tube. It only becomes equal and remains equal in the fully developed region. That is, by definition. So before fully developed region, the boundary layer is still growing. So its thickness is still increasing. It cannot be equal to the radius of the tube, which is why this second statement is false. And also, the statement 3 says that the radial velocity component is 0. That is also false because due to these, changing velocity in the axial direction. So if I take a parcel of fluid like this, which let's say is somewhere like this, yeah. So here I have, a boundary layer growing. So the and as I mentioned that the core velocity increases. So whatever velocity is coming in here in the left side, in the right side, that velocity is higher. So I'll just draw this close to the um, closer to the core, right? So as a result, there should be some leakage in order to maintain the mass flow rate in the radial direction as well, right? Because there's a difference between what comes in and what goes out in the x directions or the axial directions. So as a result, there will be a small but finite radial velocity. It won't be zero. So that is why this is also false. So as a result, the correct option to pick would be option A. There is only one is correct. And that is indeed the answer. Okay, so let's move along. We'll move on to question number 3, which is asking us which of the following is true for thermal entrance length and hydrodynamic entrance length. So thermal entrance length is given by L suffix T and hydrodynamic entrance length by L suffix H. And there are many relations given in the options below. You have to pick the correct one. So option A says it should be that LT over LH is proportional to Reynolds number, RE. Option B says that it should be proportional to the Nusselt number, NU. And option C says that this ratio, LT over LH, should be proportional to Prandtl number, PR. Or is it option D, that is none of the above, that none of these three relations given above is true? So let's take a look at the solution. It is actually option C, that is LT over LH is proportional to PR. So this is quite similar to how, the thermal, so PR, as we know, is basically uh, nu over alpha. So the more the nu, you can imagine that LT would grow, the LT would be shorter because due to higher diffusivity, sorry, the LH would be smaller. So LH should be inversely proportional to 1 by nu, uh, inversely proportional to nu. That is because more the diffusivity, the less the uh, entrance length. And similarly, the thermal boundary layer, that will also be inversely proportional to the thermal diffusivity. As a result, this follows a inverse relation to the diffusivity and their ratio as well. So if I now take LT over LH, that should be proportional to nu over alpha, which is basically nothing but our Prandtl number. So this is a simple way of showing things. There is a more involved derivation in the lectures. You can always go back and take a look at that. All right. So moving along, we'll move on to question number 4 now, which is asking us that in an internal flow for uniform wall heat flux condition, the mean temperature varies as what? So once again, I have an internal flow in a pipe like this, and the condition here is that the wall heat flux is constant, some Q dot W, that is constant all over. In that case, what happens to the mean temperature? So the bulk mean temperature. As it varies with x, and x is the axial direction here. Does it vary linearly with x, as option A says? Option B, independent of x, that is, it does not vary with x, it is some constant, or or does it vary exponentially with x, or is it option D, none of the above? That it might vary with x, but not linearly or exponentially. So let's take a look at the solution. It is option A, it varies linearly with x. So what happens in a case where there is uh, constant heat flux, at least in the developing region? So if let's say there is heat transfer from the uh, wall to the fluid, so in that case, the let's say the wall temperature would be something like this, and I'll take a different color. Or no, the initial part would be somewhat different. So it increases first, then it varies linearly. This is T wall, and in order to maintain a constant heat flux, the temperature difference between the wall and the bulk mean temperature has to be the same as well. Here it will be something else, but that doesn't matter. We will focus only on the fully developed region. There, it varies linearly with x. This being x and this being temperature. It maintains a constant slope. And most importantly, this difference, the difference between the wall temperature and the mean temperature, this is always constant. That's what ensures that the uh, heat transfer uh, or the heat flux is uniform. So that is why it varies linearly with x. All right. So let's take a look at question number 5, which is asking us that which of the following is a favorable pressure gradient for avoiding flow reversal? Is it option A, dpdx less than 0, option B, dpdx greater than 0, option C, dpdx equal to 0, or is it option D, none of the above? Now here the underlying assumption that P is a function of x only, that is pressure varies only in the axial direction. So in that case, which of the following can be called as a favorable pressure gradient, and it also avoids flow reversal? Let's take a look at the solution. It's actually option A, dpdx less than 0. And that is because, so if I, once again, I have a flow scenario like this, where there is a flow going on from left to right, and if the pressure gradient is less than 0, then if I take a fluid parcel like this, which is moving this way, it is actually moving from a region of, higher pressure to lower pressure. So it will undergo some acceleration due to this pressure difference. Albeit there can be, shear forces opposing that as well, but if they are balanced, then there will be no acceleration. But anyway, this is what a favorable pressure gradient means. Now, what happens as a result? So if there is a favorable pressure gradient, the boundary layers do not become too thick, right? So boundary layers becoming too thick is one of the leading causes of flow reversal. So in case there is a adverse pressure gradient, which is the opposite of this, which is dpdx greater than 0. So then the boundary layers will grow very rapidly, and as a result, some fluid parcel, so as a result, some parcel of fluid which is moving in this direction has a chance of reversing its direction, meaning it might roll over like this. And boundary layer separation also is another issue. So if I have an adverse pressure gradient, a boundary layer which was like this eventually, you know, becomes like this. This is known as the point of inflection, and further downstream, it becomes like this. So this is exactly what flow reversal means. And this kind of a situation arises in case of a adverse pressure gradient, not in the case of a favorable pressure gradient, where dp dx is less than 0. All right, so moving on, we'll move on to question number C now, which is asking us the fanning friction coefficient for a Hagen quasi flow is given by what? CF is equal to 16 over RED. So the Reynolds number is taken with respect to the diameter D. So is it CF equal to 16 over RED? Is it option B, equal to 32 over RED? Or is it option C, CF equal to 64 over RED? Or is it option D, none of the above? Once again, Hagen quasi flow is nothing but flow in a circular tube, obviously fully developed. In that case, what is the fanning friction coefficient? And the fanning friction coefficient CF is, as we know, is given by the wall shear stress over half rho u infinity squared, where u infinity is the free stream velocity or the mean velocity. In this case, this is the mean velocity. So we know that in a Hagen quasi flow, our uh, velocity u is a function of r given by u max into 1 minus r over r naught squared. So that u max also happens to be twice u mean. So we'll use that 1 over r by r naught whole squared. So using this, let us find what the shear stress would be. That is nothing but mu into dou u dou r at r equal to r naught, that is at the wall. So we'll just take this derivative now. So mu into 2 um, and inside 1 becomes 0 minus I have a r naught squared and r squared becomes 2r, and I'm taking this at r equal to r naught. So this gives me 1 r naught. This cancels out. So finally I get minus 4 into mu by r naught. Right. So now also we'll make another assumption, another small calculation here that since RE has to be in terms of diameter, so we'll convert this radius to diameter. So this just simply becomes, and we'll drop the minus also for the time being, right? So this basically becomes 8 mu over D, where simply D is equal to 2 into R naught. Diameter is twice the radius, that's all. So we'll just plug them in over here. So CF now becomes 8 mu by D. I have a half here, so I'll bring this 2 up to the numerator. So 2 multiplied by this. And I have rho, I have squared. I'll cancel out 1 and okay. So the rest of the things you can see that rho d over mu, that's nothing but the Reynolds number, and 2 multiplied by 8 gives me 16. So this becomes 16 RED, where RED is basically rho diameter by mu. So it should be option A, that is 16 over RED. All right, so moving on. Move on to question number 7, which is a true or false type of question. The statement is that flow variables meaning all the components of fluid flow velocity. So UR, that is in the radial direction, UX, that is in the axial direction, and UV, which is the azimuthal velocity, like a swirling velocity, if there is one. So the statement is that flow variables are independent of angular variation. Angular variation means variation along phi, the azimuthal direction, in an axisymmetric flow. Is that statement true or is it false? So let's take a look at the solution. It is actually true. So by definition, axisymmetry means that around the axis there is a symmetry. So if I, instead of drawing the entire flow field, if I just take one cut section like this and rotate this, that would give me the entire uh, three-dimensional velocity field. So there is no variation in the phi direction. That's what by definition axisymmetry means. So obviously the flow variables, they're independent of the angular variation in case there's an axisymmetric flow. So what can we tell about these flows mathematically? So first of uh, all the flow variables, that is all the components of u, ux, ur, u phi, even if it is there, and also pressure. These are all uh, functions of, these can be functions of x and r only and not of phi. This cannot be a function of phi, first of all. Secondly, all the derivatives with respect to phi, they also disappear. So if I take any derivative with respect to phi, they will be zero because they don't vary along the phi direction. They're independent of it. So these mathematical properties become very helpful in simplifying the governing equations, be it the Navier-Stokes equations or the energy equations which are necessary for convective heat transfer, to much more simplified equations which we can solve and get exact solutions out of. And this axisymmetric assumption is a fairly a good assumption most of the time. All right. Okay, so moving on, we'll move on to question number 8. Once again, a true or false type of question. It is asking, the statement is that in a fully developed temperature region, the fluid temperature varies radially and axially. Is that true or false? Fluid temperature being T. Does that vary radially and axially? Is that true or false? Let's take a look at the solution. It's actually true. So you might think that this is false since our idea is that in the fully developed region there must be no changes. But as it turns out, only the non-dimensional temperature does not change, which is P equal to temperature T minus T infinity divided by T wall minus T infinity. This only varies radially, in fact. So this is only a function of R and not of X. But if we look at temperature alone, that usually varies with the axial direction as well. So if I draw a few profiles, so let's say at some section, I have a profile like this of temperature T. Once again, this is my R direction, this is my X direction, radial and axial. So down the line, if there is heat transfer, the temperature will actually increase. The shape might not change. If I normalize temperature and find out phi, that might not change, but the absolute temperature, that does change due to heat transfer. So even in the fully developed region, the fluid temperature does vary in the radial as well as in the axial direction, which is why this statement is true and not false as it might seem intuitively. All right. Okay, so moving on to question number 9 now, which is a numerical type question. So there are some information given to us. So it says that water flows through a circular tube with a mean velocity of 0.2 meter per second. The mean inlet and outlet temperatures are 20 and 80 degrees Celsius respectively. So I'll just draw the figure over here. So I have a circular tube like this, right? It has a mean velocity of 0.2 meters per second. The inlet temperature is 20 degrees Celsius. The outlet is 80 degrees Celsius. The inner diameter is zero point 0.5 centimeters. So there's an inner and outer diameter. I'll draw that. The inner diameter is zero point 0.5 centimeters. The length is 10 meters. The wall is heated by a heat flux of Q equal to zero point 0.6 watt per centimeter squared. So then consider the flow to be laminar and fully developed. The maximum wall temperature in degrees Celsius is how much? Then all the fluid properties are also given. See, there is a lot of information given, but that might not be necessary to use all the information. We just need to find what the maximum wall temperature is. So if we go back to one of our previous solutions where we saw that for constant heat flux, which is true in this case, the heat flux is a constant number, zero point 0.6 watt per centimeter squared. So in that case, we know that the mean temperature, T mean, varies linearly with x, right? And wall temperature is given as 80 degrees Celsius over here. So I'll use a different color for that. So the wall temperature is given, and at this point it is 80 degrees Celsius. That is the maximum. So it makes sense that wherever the maximum wall temperature is, the mean temperature will also be maximum over there itself. This we have to find. We only need to find the maximum wall temperature. Oh, sorry. So the maximum bulk mean temperature is given, that is 80 degrees Celsius. The wall temperature we just have to find out. And for that, all these details are not really necessary. So basically, we can use Newton's law of heating, which is not Newton's law, just the convective heat transfer formula. It is H into T wall minus T mean. Just this. Mind you, Q is given and H is also given. T mean is also given. We just need to find the wall temperature TW. So this will simply become Tm plus Q dot wall over H. Tm we know is 80 degrees Celsius and Q dot wall is zero point 0.6 watt per centimeter squared. So we have to convert this zero point 0.6. In order to make it meters squared, I need to multiply 10 power 4 and H is 560. So this would be something like 600 by 560. So that is, I will just do the calculation. Give me a second. Sorry, not 600, 6,000. So 6,000 over 560 is something like 10.71. So if I add 10.71 to this, it just becomes 90.71 degrees Celsius. We can approximate this to be 91 degrees Celsius. That's enough. So that is the maximum wall temperature. All right. So moving on, we'll move on to question number 10, which is asking us that which of these flows, there are different flow scenarios given in the options. So which of these flows has the lowest friction coefficient CF? Once again, fanning friction coefficient CF. Is it option A, plane co-wet flow? Is it option B, plane quasi flow? Or is it option C, Hagen quasi flow? So I'll define what I mean. The plane co-wet flow is something like this. I have two flat plates, and one of those plates is moving with a velocity u. So I have a velocity profile, something like this, a linear velocity profile that develops. Then in a plane quasi-flow, these two parallel plates, they are held stationary and there is a pressure gradient that is applied. And as a result, I get a 2D parabolic velocity profile like this. And in case of a Hagen quasi-flow, I have a circular pipe. And once again, there is some pressure gradient which creates a parabolic profile like this. Among all these three options, so this is option A, this is B, this is C, which one has the lowest friction coefficient, CF? So for Hagen quasi-flow, we already calculated the CF that turned out to be 16 over RED, given Reynolds number is taken with respect to the diameter D. Then in case of a plane quasi-flow, if we calculate, we will see that the CF becomes 12 over REH, where H is the separation between these two flat plates. And for a plane quet flow, this CF is equal to 8 over REH. Once again, H being the separation between these two plates. So just numerically, as it turns out, and given that the Reynolds numbers are all the same, it's the plane quet flow which has the lowest number among them. So option A should be the correct answer. So that was the last question of today's session. We'll meet again next week. Thank you.